How can a single asteroid impact lay waste to an entire planet? A team at NASA's Ames laboratory in California hunts for clues. Peter Schultz is the authority on asteroid impacts.
Asteroids have changed the Earth. They've changed the life on the Earth. The Chicxulub impact was not that rare an event. So it's critically important to understand what happened then, just to be able to understand what might happen in the future.
Peter uses a custom-built gun to simulate asteroid impacts. He will fire a small ball of aluminum at over 12,000 miles an hour directly into his model of the Earth to recreate an asteroid strike.
We want to watch what happens, then we get to understand what may have happened 65 million years ago.
You're clear right now.
Okay, lock and load.
High voltage is good.
Oh, gorgeous. There's this big giant plume that goes straight up. And this plume is heading straight out into outer space.
This kind of impact shoots dust and vapor straight up, leaving a relatively small circular zone of debris.
For a vertical impact, a lot of the energy occurs locally, sending it up and out, and that disappears. Most of the ejecta will land right in that region.
But some dinosaurs live thousands of miles away, on the other side of the planet. How could this impact affect them?
I don't think this is what happened to Chicxulub.
So what did? Peter believes the impact site holds vital clues. Hidden beneath the Gulf of Mexico today lies the Chicxulub crater. Most small craters are circular, but the Chicxulub crater is giant, and its inner rim is shaped like an egg. Under its skin, there is a layer of lighter-colored debris and shattered rock. This is fallout from the impact. It is far deeper on one side of the crater, suggesting the asteroid struck the Earth in an unusual way. Peter believes this is evidence that the asteroid hit not head-on, but at a shallow angle to the Earth.
We're going to see what happens when we come into low angle. We're going to be coming out of here.
Rolling.
The vapor plume now isn't just simply going up and out. It's actually going downrange. It's kind of like having a nuclear explosion moving along across the surface and expanding.
The low-angle impact produces a different kind of crater. It's egg-shaped, just like the crater at Chicxulub.
That's much more serious than a vertical impact. For life on Earth, it would have meant that there was a zone of death and destruction.
Good evening, everyone. I'm Professor Andrei Zvelindovsky. I'm head of School of Mathematics and Physics of University of Lincoln in the United Kingdom, which is also a place where the famous cathedral is, which is just the image you can see behind me. And I'm joined today with Professor Don Kurtz. We are very happy to see everyone who came to this fifth Astro-Chat with Professor Kurtz. And I see already quite a few people joined. Hello to everyone. So I'm watching as you type in your live chat. Before we start, I'll just say a few words in case you came for the first time to this Astro-Chat. Don was born in America, in San Diego, and he has a distinguished career basically across the globe. First, after moving from America to South Africa, he spent about a quarter of a century there in academia before moving to United Kingdom, where he spent also about a quarter of a century. Don is author of hundreds of scientific papers, of a classical nowadays textbook in astroseismology, and in his career he also served as vice president of Royal Astronomical Society. Don is a prolific public speaker all around the world with various talks on astronomy and astrophysics subjects. At this moment of time, he is extraordinary professor in Northwestern University, South Africa, and also visiting professor here, University of Lincoln. And thanks to internet, we can talk to Don, who is physically right now in South Africa, and I'll give now floor to Don. Thank you, Don, for joining us.
Thank you, Andrei, and good evening, everyone. Before I start the talk, I need to give you a bit of a heads up. I am in South Africa, and we have got power problems here in South Africa with our national power system. I am currently in a rolling blackout, so I have no power in the house, and I'm running this presentation to you through my phone, and I have a limited amount of data left. And I hope that I can get through the talk before my phone actually runs out of data. But if I disappear, you'll realize it's because I've got no power and the phone has run out of data. So with that, the movie that you just watched, made at NASA Ames Research Center, was with Peter Schultz. And one of the reasons I put that in is that 50 years ago, Pete Schultz and I were graduate students at the same time at the University of Texas. His PhD thesis was the biggest PhD thesis anybody ever saw. He had to be put into 2 volumes. It was 800 pages. And back then we typed our own PhD theses on little manual typewriters. And his was on the geology of the moon. You could see there he has become an expert on impacts. And particularly he was talking to you about the Chicxulub impact, the end of the Cretaceous. And we'll talk about that during this talk. And so let me now go to my screen share. It says include, I got an include computer sound, so I'm talking to Andrei right now. We might even get sound out of this. So do you have the shared screen, Andrei?
Just wait a second.
You're not seeing it yet?
Probably takes a few more seconds.
It shouldn't take any seconds at all. It should do it immediately. Oh, hang on, I can see the possible problem. There we go. Has that done it?
Yes, now we see it.
Okay, there we go. You got it, Andrei. Andrei?
Yes, it's all fine, yes.
Okay, thank you. All right, good evening, everyone. This talk is about asteroid impacts on the Earth and the effects they have on us today, and of course the effects that they've had in the past. When the solar system formed 4.65 billion years ago, a disk of material formed around the sun. Now this is a star that's doing that right now. This is a cooler star, a little bit smaller than the sun. This is the Planetary Data System number 70 star. And it's being imaged with the ALMA millimeter or radio telescope in Chile. And what you're seeing here is there's a star in formation, and here's a disk that is formed around it. And that disk is full of dust and rocks. But in the inner part of this forming solar system, it's already formed 2 planets. You can see one of them there. And that planet, in fact, has got its own disk around it where it's forming a moon. And as that planet moves around the star, it's sweeping up all the leftover rocks in the disk. And so during the first 400 million years of the Earth's life, there was heavy bombardment, same with the moon, with asteroids and rocks crashing together to eventually to form planet Earth. Those were largely swept up in the first 500 million years. And for the last 4 billion years, there have been far fewer impacts because there are fewer asteroids to hit the Earth. But there are still many around. Here's a schematic diagram. And just a moment, I need to create a laser pointer here so you can see. Here's a schematic diagram with the sun at the center, Mercury, Venus, Earth, and Mars in orbit. And then way out here, Jupiter's orbit. Now, between Jupiter and Mars, there are thousands of asteroids. And a few of those cross the Earth's orbit. And those are the ones that we're interested in tonight and, of course, concerned about. Because if they cross the Earth's orbit, someday they will pass through the Earth's orbit just as we're at that point. And we will collect them in a titanic explosion. These are pictures of asteroids that have been taken by satellites out in the asteroid belt. These are not Earth-crossing asteroids, but it gives you an idea of what they look like. They're gigantic rocks. Here we're looking at Lutetia, which is over 100 kilometers across. This would be more than an extinction event if that hit the Earth. There's nothing that big that crosses the Earth's orbit now. The largest asteroids we know of that currently intersect the Earth's orbit are about 5 kilometers in diameter, and those would be an extinction event if they hit. The smaller ones would just be a big disaster. And one example of that is the asteroid Bennu, B-E-N-N-U. Bennu is about 500 meters across. And being so small, it's got very weak gravity. And instead of looking like a big rock, it's just a pile of rubble. And there's been a US space mission orbiting that now for some time. It's called OSIRIS-REx. And OSIRIS-REx is just an acronym for a lot of things about observing and collecting some material from it. Let me set this in motion. OSIRIS-REx. Bennu rotates in about 4 hours. And the mission was sent there to land on the surface and collect a piece of the asteroid and bring it back to the Earth. And in fact, that happened just recently. The mission landed at this Nightingale landing site right up here, and it collected some amount of material. It's not certain how much it got. It had to punch into the ground into a container and then seal it up. It'll be somewhere between a minimum of 60 grams and a maximum of about 2 kilograms. We're hoping for 2 kilograms, probably 1 kilogram is likely. That mission has left the surface of Bennu and it's on its way back here to the Earth. And on the 24th of September, 2023, it will drop that container down through the atmosphere. Parachutes will be set out and it will come down in the desert in Utah to be collected. And then we'll be able to study a piece of the original formation of the solar system back from the early years. This is a remnant from that original bunch of rocks that you saw in the disk of the other star I showed you just a moment ago. Asteroids do hit the Earth. In 2013, one entered the atmosphere above a town called Chelyabinsk in Russia. And dash cams, video recorders caught the entry. It was early morning, 9:20, but in wintertime, the sun's not up yet. It was actually brighter than the sun momentarily in the sky. And there is to show you where it is. Here in Chelyabinsk, this is Russia stretching across here, the world's largest country by far. There's Chelyabinsk, and that meteorite exploded in the atmosphere 30 kilometers above the ground. Fortunately, it was so high up that minimized the damage, although there was still plenty. Just to remind you, Andrei is originally from Odessa in the Ukraine, and that's just off the edge of our map over here on the left. So when the Chelyabinsk meteorite exploded 30 kilometers above the ground with that great flash, people saw the flash and they came running to their windows. They went outside to watch it. Something fantastic had happened. And what they weren't thinking was that the blast wave was coming. It took a while to get to them, but when it arrived, they knew about it. Let's watch what happened.
А что думаешь, может, спутник там уже же падал, они сказали...
Most of the injuries were from flying glass. This woman's watching some colleagues who've gone to the window to see what happened. The blast has arrived and blown the windows out. And since the meteorite broke into pieces, there are multiple blasts, and they're now wisely getting out of the room. This couple are supposed to be working together. It looks like they're having a nice chat with each other when their window gets blasted out. There's no sound with this one. And he chivalrously there goes to help her leave. This is a classroom. It's Friday. And this is a job interview.
Это обращение в нашу справочную службу, которые зафиксированы за январь месяц. Где?
Oh, very frightening. Parts of it came down, crashed through the ice into this lake. You can see in the lower right, there's a piece. Many pieces have been picked up. Over 650 kilograms were collected from that lake. And it's a very important piece of the original solar system that has been found with this great explosion. It had the explosive power of 440 kilotons of TNT, more than 20 times the power of the World War II atomic bombs that were dropped on Japan. Here's another one that came down in Peekskill, New York, 1992. It was a night of high school football, and lots of people were filming football with their cameras, and so there were many videos made of the meteorite breaking up and coming in. We know where it landed. It hit this car. This car belonged to a young woman named Michelle Knapp. She was 17 years old. It was her first car. She just spent $300 on it and was very proud of her 1980 Chevy Malibu when this rock, you can see it in the bottom there, crashed through the boot of her car and destroyed it. Now we can feel sorry for the girl having her first car destroyed until we know that she sold the meteorite for $50,000 and she sold the car for $25,000. You might wish this would happen to you as long as it doesn't actually hit you. The car is now in a museum, but it's available. There's a website for it, and you can actually hire it to come to your event if you like for a price. Just last month, 3rd of October, a meteorite crashed through a roof here in Golden, British Columbia in Canada. There's Vancouver Island. There's Seattle in the United States. It crashed through a woman named Ruth Hamilton's roof during the night. The sound of the object coming was heard by her dog, and it started barking, which woke her up, punched through her roof, and then landed on her pillow right next to her head. It weighed about 1 kilogram. If it had hit her in the head, it would have killed her. So she was fortunate that it didn't actually hit her. She's now sent it to an expert on meteorites at Western Ontario University in Ontario, and he will study it, and then she's asked to have it back to keep it as a keepsake after that. The biggest event in the last more than 100 years was the Tunguska event, which was in the morning of June the 30th, 1908, and it too hit Russia. You may think Russia is unfortunate, but the meteorites are not targeting Russia. It's just a big country, so it gets its fair share. And that meteorite hit over the stony Tunguska River north of Irkutsk here in Siberia. I've been to Irkutsk a few times. It's an actually beautiful city. For those of you who think Siberia is all just cold and tundra, the big cities of Siberia, Irkutsk and Novosibirsk over here, Yekaterinburg, Kazan are beautiful modern European cities, pedestrianized, big, beautiful buildings, people out strolling, and it was a surprise to me when I first went. There's the remnants of what happened in 1908 when the meteor hit above Tunguska. It blasted the trees flat for 30 kilometers in all directions. It set up a shock wave that traveled around the world many, many times. The blast was heard all the way over in Western Europe. That's the biggest one that we've had in many years. Now, over 100 years. Here is an atomic bomb test of an atomic bomb that was twice the size of the one that was dropped on Japan. That's a mountain you can see in this movie we're about to watch. And it, of course, it's exploded close to the ground, not 30 kilometers up like the Chelyabinsk meteor, which was 20 times bigger than this. But this will give you the impression of the terror that comes with one of these explosions. We'll hope that nobody ever uses these atomic bombs. Eventually, we will get hit by meteorites again. And if they're big enough, then this is the kind of destruction that comes with great shock waves, traveling across the ground, churning up the dust, the dirt, blasting everything flat. And of course, there's also a fireball. The Chelyabinsk meteor was brighter than the sun. Really big ones are so bright they just set fire to everything. Here is a report of fireballs over 30 years, 1988 to 2018, with a Mercator projection map. They're color-coded for size. There's Chelyabinsk up here at 440 kilotons. You can see that the Earth is equally hit all over the planet. No place is preferentially hit. Mostly they hit in the ocean, of course, because the ocean covers most of the planet. Russia gets more hits than other countries simply because Russia is bigger. Here's some idea of how often these hit. Half a kiloton impact, that's a pretty big explosion, but not disastrous, every couple months. 10 kilotons, that's a major bomb type explosion every 2.5 years. Those are mostly in the ocean. Every 5 years for something as big as the World War II atomic bombs. And Chelyabinsk, well, Chelyabinsk is probably a once in 50-year event at 440 kilotons. Chicxulub, 65 million years ago, was the big one over the last 100 million years. A meteor 5 to 10 kilometers in diameter hit in what's now the Yucatan Peninsula of Mexico. It exploded with the power of 10 to the 8th megatons of TNT. That's 10 to the 8, 100 million hydrogen bombs. It would have melted the rocket, punched down into the crust 20 kilometers under the surface. And the fireball set fire to North America, burnt North America to the ground. It sent a shockwave around the world in a flash. India, which was not attached to Asia at that time, but was out in the Indian Ocean, was also set on fire. And dust, soot, ash, water vapor filled the Earth's atmosphere, and it went dark, and it went dark probably for about 10 years. There's where the Chicxulub crater is. This is the Gulf of Mexico. Texas is over here. There's Florida. There's where the meteor hit. And the tsunami from that went over 1,000 kilometers inland in Texas. And you think, as you're sitting there now in Lincoln, for most of you, although not all of you, well, at least Florida and Cuba are there blocking the tsunami. So England's going to be okay? No way. Here's an animation of what that tsunami would have been like. The white areas are areas impacted by the tsunami. In comes the impactor, 20 kilometers per second. It explodes with the power of 100 million hydrogen bombs, and out goes the tsunami across the oceans, up the Orinoco River, up the Amazon River, there right across the top of Lincoln. It sweeps across the southern part of the UK, the Low Countries in Europe. Major destruction all over the planet. And that caused the extinction of 75% of all species living on the planet. It wasn't just the dinosaurs that died out. Every four-legged animal bigger than 25 kilograms went extinct with this. 75% of the plants went extinct. The sea life went extinct. This was one of the major extinctions. Now, there were some small mammals that made it through. The birds made it through too. This is Gary Larson's view of it, the cartoonist. Here are the big tough dinosaurs, the Stegosaurus, some other nondescript dinosaurs here, who are laughing at this stupid little mammal here, which is tiny, it's covered in fur, and it looks pretty dumb to a big dinosaur. But come the darkness and the cold after the Chicxulub asteroid impact, the dinosaurs were driven to extinction by just the cold. The plants died, the animals died. But the little furry animal, the little furry mammal, which was our ancestor, managed to make it through the winter. And when the sun came back and life started coming back again, the dinosaurs didn't dominate, and the mammals and the birds then expanded into the environment. Now, just hold with me for a second, folks. I want to just see how my data's doing in the hopes that I'm not going to lose you somewhere. All right, okay, it looks like I'm going to be okay. I'll worry about that again in a bit. The biggest impact crater on the Earth that we know of is called the Vredefort impact. It's in South Africa. It's up partly in the Free State, partly in what's now called Gauteng. Used to be the Transvaal across the Vaal River. This is the Vaal River running across the picture. And there you can see the crater rim. Now that's the inner crater rim. The outer crater rim for this is over 300 kilometers in diameter. It's twice the size of the Chicxulub crater. And so this was a much bigger impact 2 billion years ago. Of course, 2 billion years ago, there was no life on the surface of the Earth. There were no plants, there were no animals. There was life in the sea, but we don't know to what extent this caused a major extinction. I was there just last week. One of my appointments, Andrei told you about, is at Northwest University in South Africa. We have 3 campuses, and one of them in Potchefstroom is only 50 kilometers from this site. And I took the opportunity to go tour the site with the world expert on it. He's Professor Franz vonders here from Northwest University. He and 2 of his colleagues were the ones who had this declared a World Heritage Site. And here we're standing with the crater. I've taken a panorama here in the background. There's the inner crater, not the outer one 300 kilometers away. And we're looking at a map of the crater as he's explaining what happened to us. In the picture also is Professor Tebe Madupe. He's the Dean of Science for Research at the Northwest University campuses. He also was my PhD student at the University of Cape Town 25 years ago, which is how I came to have an appointment at that university since he's Dean of Research. And this is my wife, and we are touring this meteorite impact. This is called pseudotacholite. It happens in a variety of ways, but you get the most spectacular examples of it with a meteorite impact. The big pieces you see here are the original granite that was present when the meteor hit. The black that you see is a very, very fine glass dust that came from the pulverization and the melting of the granite with the impact. And at this particular game reserve right here, you can see a nice piece of it which has been polished up into a beautiful piece of rock for the entrance. I would love to get this stuff to make a new kitchen with it, but currently it's no longer being mined and processed by anybody. Beautiful type of granite with the clear signature of a meteorite impact. The other interesting thing is that you probably know South Africa's perhaps biggest piece of its economy is gold mining. And the gold originally was about 15 kilometers underground, but this meteorite impact 2 billion years ago turned over the layers and brought the gold layers up to within just a couple of kilometers of the surface where they can be mined. And so South Africa's economy is actually dependent on the fact that this meteorite hit 2 billion years ago. We've seen this happen on other planets. 1994, a meteor hit Jupiter. Well, 2 years before this meteor, comet Shoemaker-Levy, passed by Jupiter, and the tides of Jupiter tore it to bits. This is a real picture. This is a Hubble Space Telescope picture. And these are all the bits of the meteor coming in 1994, about to crash into Jupiter. The biggest piece, called the G piece, was 2 kilometers in diameter. Now, Jupiter's got a black spot on it, but that's the shadow of the moon Io. I talked to you about that in the last talk when we talked about Jupiter, and that's what that is. As these came in, they crashed into Jupiter at 60 kilometers per second, and the Hubble Space Telescope caught the explosion. It was just over the limb. It hit the other side of Jupiter, but there, over a matter of minutes, you can see the fireball, much bigger than the Chicxulub fireball, coming up out of the atmosphere of Jupiter from that incredible explosion of the G impact into the atmosphere of Jupiter. It created a scar that I could see even through my small telescope observing it for a couple of months afterwards. And there you can see the debris scar in the gas atmosphere of Jupiter. Remember, no solid surface for Jupiter. So many of you will have seen these Hollywood movies. Hollywood loves asteroid impacts for its films. There was Deep Impact, Armageddon, Greenland recently, where in comes the meteor, and it's either going to be an extinction or close to extinction event, and of course the heroes have to try to survive it. And you mostly will have seen some of these movies, I think. I have to tell you that I use them for teaching undergraduates, because in one of the movies, the astronauts go out and they blow up the asteroid, and then it all just arrives at the Earth in pieces and harmlessly burns up in the atmosphere. And I have to tell you, no way. All those little pieces still deliver all the original energy. You cannot protect yourself by blowing it to bits. It's still going to deliver all of its energy. It doesn't matter whether it's in one piece or lots of pieces. What you have to do is deflect it. Do we have the ability to do that? Well, we're trying to get it. Here's our last slide before we go to questions. The double asteroid redirection test is going to be launched on November the 23rd in California. That's November the 24th in Lincoln in the UK. It will be launched at 6:20 a.m. GMT on the 24th of November, and there will be live coverage of the launch on NASA TV. I plan to be up to watch that. And the idea will be this satellite will go out to a small double asteroid. The biggest piece is 780 meters across. The little one's only 150 meters across. Still would be a disaster if it hit the Earth. And it is going to smash into the surface of that asteroid at 15,000 miles an hour. And then we're going to see if it actually changed the orbit of the asteroid and made it move a little bit, because you don't have to push the asteroid very far to make it miss the Earth if you catch it early enough. So that's the idea, not go out and blow them up, but go out and just nudge them and make them miss. With that, I'm going to stop. Let's take questions and see what you got that you'd like to hear about. So we'll stop the screen share here. Andrei, tell me when we've succeeded in doing that.
Yes. We're now back on screen, two of us. So thank you very much, Don, for illuminating talk as all this. Now we open for questions. We have just 1 minute less than half an hour. And everyone can type questions just below in a live chat of YouTube video, and then we'll proceed with that. So here there is a first question arise from Anthony Bloxham. Great talk. What can you tell us about the mysterious Tomsk Crater?
Oh, Anthony, I can't tell you anything about that. I don't know about the Tomsk Crater. While we wait, Tomsk Crater, I'm going to do what you would do. I'll just look on the internet here quickly. Tomsk Crater, discovered in 1949 in Russia, another one. And it says it's a peculiar rock formation. It's again in the Irkutsk region. Thank you for pointing that out to me. I'm looking at a picture now, which is quite beautiful. And the crater has a diameter of about 160 meters. So it's substantially smaller than the Barringer meteor crater in Arizona, which is the famous 1 kilometer diameter meteor crater. Okay, thanks for the question. That was a new one to me. I'll read that further later when this is over.
Yes. Okay. As questions come in, I would like also to ask kind of one question from me. You taught astrophysics and astronomy for lots of years, and occasionally there is a question comes from outside of astrophysics astronomy area. Is it useful really subject? Does it bring anything to us, to everyday's life? And I think this talk might give us a very good answer to that.
Andrei, do you know, maybe I should do one of our Astro-Chats just giving the many answers that I have to that question. But yes, here's one case where possibly it does. If we can develop the technology to detect these asteroids, we can now prevent an extinction level event and prevent humans from going extinct. That seems like a pretty practical use. But since you've asked that, let me tell another story. When I was a graduate student, I had a colleague at the University of Arizona who was also a graduate student there by the name of Pete Worden. And Pete, when he finished his PhD, went into the US Air Force. He became a 2-star general. He ran Ronald Reagan's Star Wars program, and his specialty is near-Earth asteroids. He became the director of that NASA Ames Research Center. And a few years ago in Hawaii, I was observing with the big Japanese 8-meter telescope. And at breakfast time for me, lunchtime for everybody else, just getting up after a night's work, I spotted him in Halepahaku, the stone house where we stay on Mauna Kea, and I cornered him. He was there with the governor of Hawaii and a bunch of other important people showing them around. But I cornered him and I said, Pete, you like to blow things up. I think you like bombs. I'm worried you're going to develop the technology to deflect an asteroid and go out and get one that wasn't going to hit, deflect it, make it hit, and get a much bigger explosion than you can get from your hydrogen bombs. I said to him, I'm more scared of you than I am of the asteroids. He laughed and he said, look, don't worry. If it's aimed at the Earth, if you push it in any direction, it'll miss. If it's not aimed at the Earth's just too tiny a target. We can't do it. So I was reassured with that answer until I thought about it as he left, and I realized he was thinking about this. Do we want to put the power into people's hands where they could actually produce a mass extinction at will? That's a political question, not an astronomical one.
Thank you, Don. We have now several questions arrived. Are there other ways of diverting asteroids? A question from Roger.
Are there other ways? Was that the question?
Yeah.
Yes, Roger, there are. Besides deflecting them by just crashing into them, another possibility would be to, say, land a rocket on the surface carrying fuel, but land it upside down, and then just fire the rocket and push. So instead of crashing into it with an impactor, you could land on it and then push with the rocket to just try to nudge it aside. Another thought people have had is maybe paint one side white and use the solar radiation pressure. If you've got enough time, that might help. The problem is that asteroids rotate, and if they're rotating, you might have trouble choosing a side if the asteroid's spinning too quickly. So people have been thinking of different ideas, but the main ideas are either impact or landing on the surface with a rocket and then using the rocket to push on it.
There is a question actually related to light from somebody with nickname Brown Bottle. The use of high-powered lasers to use the momentum of photons to also nudge it out the way slowly over time. Is this feasible, or the technology out of reach yet?
Excuse me, Brown Button. The answer is the technology is not out of reach, but it's not adequate to do the job. You may have been hearing about this in two places. One is in a previous Astro-Chat, I talked about the Breakthrough Starshot project, where lasers on the ground would be shined onto nanosatellites and accelerate them up nearly to the speed of light to go out to Proxima Centauri to look at its planet. Those are tiny, those aren't big rocks. The other place you may have heard about it, there's been some discussion of using lasers from the ground to bring down orbiting debris. We're getting so much clutter up in space that it's getting dangerous for the satellites that are working. And so the idea was to use the lasers to bring the satellites that are no longer useful into the atmosphere where they will burn up. But the radiation pressure isn't bringing the satellite down. What's happening in that case is the laser is evaporating material off the surface of the satellite, and that evaporative material shoots off the surface and acts like a little jet and takes a little bit of energy away from the orbiting piece of material. So you only do this as the materials, as the orbiting satellite's coming over the horizon. You shoot at it when it's coming towards you, and then the vaporized material comes in the direction it's flying, and that robs it of some energy and it drops into a lower orbit. So even if we could develop the lasers to shoot at these asteroids, there's no way that they would have anywhere near the light pressure to do anything noticeable to them.
Thank you. There is a question from Philip Cox. What is the big advantage of spacecraft collected samples over collected meteorites?
Oh, okay, that's a very good question. And if this is Philip Cox, is this possibly Philip Cox who long ago took an astronomy course from me? You can tell Andrei that by typing in if that happens to be the Philip Cox you are.
Yeah, we'll wait.
No, I'm going to answer the question now. Phil, it's because the asteroid collected is pristine. An asteroid, a meteorite that has fallen to the Earth, has been transformed by the heat of entering the atmosphere, but it's also now been contaminated. It's been in contact with the Earth's atmosphere, it's been in contact with the Earth's ground, and it's now been contaminated by material that's not pristine original solar system material. So we want to go out and get a piece of the solar, and also the Earth's totally transformed, so the rock on the Earth is not like it was when it formed. We want to get a piece that was like the solar system before anything transformed the rock on the Earth from all the things that have happened here. So it's original material and not contaminated.
Thank you. And Philip Cox replied, yes, the same.
Oh, well, nice to hear from you, Phil.
And now this question from somebody with nickname Hi Holly. What is more dangerous, an asteroid strike on land or in the water?
Oh, Hi Holly. Do you know, it depends on the size of the asteroid we're talking about. If we're talking an asteroid like Chelyabinsk, if it hit the city of Chelyabinsk and exploded with 20 times the power of a World War II atomic bomb, it would obliterate Chelyabinsk. If it hit in the ocean, it would set up a tsunami and there would be some coastal flooding, but it would be far less damage. But that's a relatively small one. What about something the size of the Chicxulub impact, 5 to 10 kilometers in diameter? It doesn't make any difference. It doesn't matter. The ocean on average is only 4 kilometers deep, and an asteroid impact of that size, the Fridaford impactor penetrated 17 kilometers down into the crust. The Chicxulub impactor penetrated 20 kilometers down into the crust. It just blows the ocean away. It melts through. It doesn't matter whether it hits the ocean or the earth. The water can't protect you with something that big. You're going to get the same disaster no matter where it hits.
Oh, thank you, Don. There is now a question from Marisha Musheli. Hi, Don, about the DART mission. Is Didymos moonlet mean to impact Earth at all, or will the mission only the test to change the speed of the moonlet?
Right. You're right that the bigger piece of that double asteroid is called Didymos. And I don't know if that's an Earth-crossing asteroid. That's a very good question. And I don't know if it's an Earth-crossing asteroid, but the intention is only to see to what extent the smaller piece of it can be deflected, how much its orbit changes. Since you asked that, though, by the way, Bennu, the little rock pile that I showed you, is an Earth-crossing asteroid, and there's about a 2% chance it will hit Earth in the next 2 centuries. At present, its closest approach will be around 2178, if I remember correctly, and it's calculated that it will miss the Earth then. You might wonder, well, why can't we just predict this? Don't we know celestial mechanics? Don't we know the orbits of the planets and the asteroids so well we can tell where they'll be in a couple centuries? And we do for the big things. But for these small things, they get perturbed by the gravity of all the big planets, and their orbits are not regular. The orbits are somewhat chaotic is the term. It's a mathematical term, and it means it's not totally predictable. And so we cannot predict some of these dangerous asteroids precisely enough, not because we're not capable or we don't observe them well enough, but because their orbits are not predictable in a mathematical sense. It's not a lack of knowledge on our part. It's just not possible to do it. And so we're not sure if they'll hit far into the future.
And there is actually a question about gravity here and the orbits from team play. Is it possible for several meteorites to coalesce under the force of gravity?
Oh, that was Tim. Tim, that's a good question. The answer must be yes. Why do I say it must be? Well, our model of how a solar system forms, oh goodness, it just says I've got less than 100 oh no, that's okay. I've got less than 1.2 gigabytes. I'm just getting a warning. We're okay for the rest of the evening. I'm going. Sorry, Tim. You saw that disk of material I showed you in one of the very first slides around another star. So we think the solar system formed by a disk of material forming around the sun, and it would have had dust in it, small solid particles. Those then would hit and somehow stick with each other. When I say somehow, that's an unsolved problem, because mostly if you take small particles like that in the lab, and experimental astrophysicists and geologists do that, when you crash them into each other, they break into pieces and scatter off of each other. We don't quite know how to get them to stick, but we think water is the answer. If they get ice on the surface, they get a little bit sticky. Somehow or another, though, they did stick and grow into larger rocks, and then those rocks stuck and grew into asteroids, and the asteroids crashed and grew into planets and moons, and that's how the planets in the solar system formed. In the outer solar system, those rocky planets that formed were far enough out, it was cool enough that their gravity could hang on to hydrogen and helium, and they grew into the great gas giants, Jupiter, Saturn, Uranus, and Neptune. So yes, it must be true because we're here, and because the Earth's here, that asteroids can stick when they crash into each other. They can also break each other apart. It depends on the collision.
Thank you, Don. And it's questions about continuous from Ryan Pickard. Has the Earth orbit been changed by these larger impacts?
Oh, the answer is yes. Every time we're impacted by anything, our orbit changes. But you probably wonder by how much. And the answer is, well, with those large impactors, 10 kilometers in diameter, you know, if we weren't driven to extinction, it's an interesting question if we could measure the change in the Earth's orbit with that, but I would guess probably not. The Earth's orbit is highly susceptible to the gravitational tugs of the asteroids, and the people who measure the Earth's orbit measure the distance to the sun to a precision of only a few meters nowadays, and we can measure the wiggles in the Earth's orbit as it gets tugged about by the asteroids out in the asteroid belt. And so almost certainly we could measure the change in the Earth's orbit when it got hit by one of those big asteroids if we could survive it. But the effect is absolutely tiny and would have no impact on what we consider to be the Earth's orbit in terms of the amount of radiation we get from the sun.
Thank you. There is one more question. Do you think the moon was part of Earth before an asteroid hit?
The answer is some people think that. And so that is the best model for the formation of the moon. You asked me if I think that. Well, I'll go with the best model, but we're not absolutely certain. The best model for the formation of the moon is that during that first 400 million years of the Earth's formation, when there was a lot of impacting still going on, the Earth got hit by something about the size of Mars. The Earth had already solidified. The iron had settled to the core, so the mantle was depleted in iron, and the impactor blasted mantle material out, which went into orbit about the Earth, and some of that fell back to Earth, some of it escaped, some of it formed the moon. Why that particular theory? The answer is because the moon is made out of stuff like the Earth's crust, but it's depleted in iron. And if the moon formed independently at the same distance the Earth is from the sun, it should have the same fractional iron content as the Earth does, and it doesn't have the iron. The iron's mostly missing. And so it can't have formed independently out of the same material the Earth formed out of. Hence the theory that the Earth formed, it melted and the iron went to the core, and then something the size of Mars would be needed in the models to blast enough material out of the mantle to form the moon, and the moon's geological makeup is similar to the Earth's crust and its mantle.
Thank you, thank you. Now a question from Andy Ellison. Right, another idea is the gravity tractor, but the mass required would be very large and difficult to launch.
So that's true, Andy. I had forgotten about that. The idea is to get something very massive near it, which would pull it and change its orbit. I can't conceive of getting that sort of mass off the Earth with the amount of energy it takes. If we had bases on the moon, well, getting things off the moon's a bit easier, getting a bigger mass off that, possibly. The fact that the idea is out there probably means it's not totally absurd. People are working on that, but I have not looked into that in detail, and I can't add anything to your comment that that's an interesting idea.
Thank you. Now a question, it's a bit long, from Haley McCartney. Have you read Natalie Starkey's book, Catching Stardust? She focused on how comets and asteroids are being studied to understand the birth of solar system, and sparked my interest a couple of years ago.
And the answer is no, I haven't read the book. But it sounds like that's a good book, and it's great that it sparked your interest. The Earth collects about 1,000 tons of interplanetary material every day, and that also gets studied. Some of that will be cometary material, and you may be interested where most of that study comes from. From meteorites? Well, meteorites are nice. You can collect the rocks, but mostly it's studying the dust, and it's easy to get. Just go to Antarctica. The dust falls out of the sky, it falls down onto the ice in Antarctica, and the people who study it just go get a bunch of ice out of Antarctica and they evaporate, they melt the ice and then they evaporate it, and all the stuff left behind, it's mostly meteoritic dust. Not completely, unfortunately. Some of it is pollution from humans.
Thank you. Now a question from John Leventhal. Where did the material come from that made the primordial cloud of asteroids?
Was it Joan or Joanne, Andre?
Joan.
Joan, you've asked a origins question. So let's backtrack a little bit. It's not the night to do a talk on the Big Bang, but it seems there was one, and so there is a universe, and it was originally hydrogen and helium. Galaxies formed, like the Milky Way, and then stars formed out of the hydrogen and helium. The stars fused hydrogen to helium, helium to carbon, carbon and helium to oxygen. They build up heavier materials. Some of them exploded and blasted that material back out into space, so that 4.65 billion years ago, gas in the galaxy collapsed with sufficient amount of gas to form an entire cluster of stars, say like the Pleiades cluster with hundreds of stars. The sun was one of the stars in that cluster 4.65 billion years ago, and it was made of 98% hydrogen and helium, but 2% heavier stuff. And as it collapsed, it spun faster and faster and faster until it spun off of a disk of material. And in that disk was the original material out of which the dust and then the rocks and then the asteroids and then the planets formed. So there's a long chain to get to the material that was in the disk that then made the planets.
Thank you. I wanted to ask Don also a question when you mentioned about this cartoon of human ancestor and dinosauruses. Then after the asteroid hit was basically like winter came, so to say, over the planet. How do we know how long that period of was really?
Andre, the only way that can be done is by modeling, and the estimates are between 3 and 10 years. It's often referred to as a nuclear winter because if humans, primarily Russia and the United States, exploded all of their hydrogen bombs, they would create that event. Unfortunately, we do have the ability to create a mass extinction with all of the nuclear weapons if they're all set off at the same time. One hopes nobody's crazy enough to do that. So you model that, and a lot of the modeling has come from people who've been modeling what happens after hydrogen bomb explosions. So there have been atmospheric tests. You can see how much material gets pushed into the atmosphere. After big volcanic eruptions, you can watch how long it takes that material to clear. After Mount Pinatubo, 1991, took a couple years for the material ejected into the atmosphere to clear. And then you estimate how much material was blasted into the atmosphere, and then estimate how long it would take to clear, how high the opacity, how thick it would be, how much light would be lost. And the calculations, the models are probably pretty good. We don't want to really test this for real, but I would guess they're pretty good. And even three years is enough for all the plant life to die. And then the herbivores die. The carnivores have a field day because they've got lots to eat for a little while, but then they run out of things to eat except each other, and then that runs out too.
Yes, yeah, it's interesting that there is interplay of astrophysics research with this military, in fact, kind of research, and strangely enough, military research helped a little bit, it seems like, to understanding of the winter dinosaurs time. And there is one actually. Yeah,
I was just going to say to you, Andre, someday I will tell that story in an Astro-Chat. It was the discovery of how stars power themselves that led to the invention of hydrogen bombs. Do you consider that to have been a practical application of astronomy?
Let's go to the dinosaurs. There is a question from Roger. Why did small mammals survive, and how long did dinosaurs survive? Days or months?
Oh, okay. Sorry, who asked that question?
Roger.
Nobody knows the answer to that, Roger, how long they survived. The fossil record is not precise enough to be able to say how long the extinction took. And that's a major question because not everybody accepts that it was an asteroid impact that caused the Cretaceous extinction. Some people think it was major volcanic eruptions, and those were certainly occurring at that same time in India, producing the Deccan traps, which are about 2.5 kilometers deep in lava. So if we could show from the fossil record that the extinction took 1 million years, we would know it wasn't the asteroid. If it was the asteroid, then it's anybody's guess whether it's days, weeks, months. There is just, the fossil record has not got that sort of time sensitivity to answer that question. Why did the small mammals make it through? Well, the same question is, why did the birds, who are dinosaurs, but feathered dinosaurs, make it through? And some fairly large reptiles made it through, like the crocodilians. The answer is almost certainly for the mammals and the birds, because the mammals had fur, the birds had feathers, and they could insulate themselves from the cold. The dinosaurs they were not endothermic, that is, they were not warm-blooded, but they were like warm-blooded animals because they were so big, they didn't actually lose a lot of heat to the environment. But if winter comes for 3 years, they're in trouble because they can't internally heat over that time. The small mammals and birds could internally heat or at least insulate themselves, and they didn't require so much food. They only needed to nibble until things got better, whereas the big animals need to eat a lot.
Thank you, Don. There is a question from Sean Schultz. Is the generic makeup of the asteroids that have been found on Earth, or they are significantly different?
Let me see if I understand the question. The asteroids that have been found on the Earth, some of them are the same material as the primordial asteroids we've gone out to. They're just contaminated. It was thought until about 60 years ago, it was thought that most asteroids that hit the Earth were made out of almost pure iron and nickel. How does that happen? A large planetoid forms in the solar system. It's big enough to melt. The iron settles to the center and then it solidifies, and then it crashes into something else and is broken to pieces. And bits of the iron core later fall to the Earth. So the biggest meteorite sitting on the ground now is called the Hoba meteorite in Namibia. It's meters across, and a piece of the corner has been cut off, and it looks like a beautiful piece of steel. It was thought until the 1960s that most meteorites were iron nickel, because that's what's found. If you're walking along on the ground and you look down and you see a chunk of steel on the ground with a melted surface, even you and I can identify that. You don't need to be a geologist. If you find a primordial meteorite made out of rock, you've got to be able to tell that that rock is different from all the other rock around it. That's not so easy. Where did the breakthrough come? A Japanese geologist said, if you want to find meteorites here on Earth, go to Antarctica. If rocks are lying on the ice, they fell out of the sky. And everybody said, oh, well, of course. Somebody had the idea first. And so most meteorites now have been collected on the ice in Antarctica. And most of them are carbonaceous chondrites. They're chondritic is the name. They're made out of stone, not out of iron nickel. And many of them are nearly primordial, but contaminated. We still want those original pieces.
Thank you. I see another question on the kind of celestial kind of impact mechanics from Team Play. Could another piece break off the Earth in a collision of any other asteroid?
Oh, for sure. Good question. That certainly happened when the Chicxulub crater was formed, and that asteroid impact, that blasted stuff off the surface of the Earth. Some of it fell back, some of it escaped. This still happens on the moon now, and when pieces of the moon get blasted off the surface and fall to the surface of the Earth, they get melted, and they're common enough you can even go out and buy them. They're not expensive. They're called tektites. We've got a couple of dozen of meteorites that were blasted off the surface of Mars and traveled around the solar system and fell to Earth, and they're sitting in museums and they're being studied. How do we know they came from Mars? The mineral composition is slightly different, but the air bubbles trapped in them have got the Martian atmosphere, not Earth's atmosphere. And so sure, when the Earth gets hit, stuff gets blasted off the Earth. So you might wonder, did life form on Mars first and it got blasted off of Mars in a meteorite, fell to the Earth and contaminated the Earth, and we're actually Martians? Or vice versa? Really interesting questions. Sure, things can get blasted off the surface of the Earth. travel through space, land on the moon, land on other planets, come back to Earth. It happens. You can go by yourself of the moon.
Thank you, Don. Thank you. And as usual, we have more questions when we have time, and our time now arrived till the end. And also, you know, Don in mobile internet, watching every second that he is still kind of connected. I would like to thank Don and everyone who came, who listened, who asked questions. As usual, we will ask you to put comments later for this video, and we will be happy, I'm sure, to see you again in one of our future Astro-Chat with Professor Don Kurtz. Thank you very much, Don, and thank you everyone who came.
Thanks everybody for coming, and I think we'll see you next month.